In this video, we will talk about how to determine if a system of linear equations has no solution, one solution, or an infinitely many number of solutions. So there are three rules of thumb that you can use. We can say that a system of linear equations has no solution if there's a pivot entry in the augmented column. So recall that when we have a matrix, let's say 1, 0, 0, 1, 0, something like this. I'm just making these numbers up. The augmented column is this column right here. If there is a pivot entry in the augmented column, that's a dead giveaway that there is no solution to this linear system of equations. And the reason is, in this first row, we can see that the pivot entry, or the first non-zero value in the row, is this 1 right here. But in the second row, the pivot entry, or the first non-zero value, occurs right here in the augmented column. And if we want to think about it as if this column represents the coefficients for some variable, let's call it x1, and let's say this column represents the coefficients for some variable x2, this is telling us that we have 0 times x1 plus 0 times x2 is equal to negative 7. Well, there's no value that we could plug in for x1 and x2 to make this expression true, because 0 times something plus 0 times something is always 0. So this could never equal negative 7. And in other words, we would say that this system is inconsistent, or in other words, there is no possible solution. So keep that in mind. So the next rule of thumb is a system of linear equations has one solution if there's a pivot entry in each column of the coefficient matrix. So if we had something like this, and let's say this is 4 and this is 9. So this is the augmented column. The coefficient matrix is right here. It's everything that's not the augmented column. So we say that a system of linear equations has one solution if there's a pivot entry in each column of this coefficient matrix. So for example, right here, in the first row, the pivot entry is this 1. And then in the second row, the pivot entry is this 1. So each column, this column and this column in the coefficient matrix, both have a pivot entry in their column. So that means there's only one solution. And if we imagine that this was the x1 column and this was the coefficients for some x2 variable, we can see very easily that x1 is equal to 4 and x2 is equal to 9. And those are the only solutions to this particular system of equations. So there's only one solution. All right, in the last case, we say that there are an infinite number of solutions if the system is consistent, but a free variable exists. So for example, if we had something like this, let's call this a 0, 0, 3, 1, something like this. In the coefficient matrix, we can see that here's the first pivot entry in the first row, and here is the pivot entry in the second row. So when a column has a pivot entry like this, we call this a pivot variable. So this column right here, this is also a pivot variable. But if a pivot entry does not exist in a particular column of the coefficient matrix, we call this a free variable. And when there is a free variable, that means there are going to be an infinite number of solutions to the system of equations. So with these rules in mind, let's work through a few examples. Let's say we have the following matrix that represents a system of linear equations. Does this system have no solution, one solution, or an infinite number of solutions? Well, let's check out where our pivot entries are. So in this first row, the pivot entry, or the first non-zero value, is this 1 right here. In the second row, the pivot entry is this 2 right here, the first non-zero value. And in the third row, our pivot entry is right here, this 1. So we can see that each column in our coefficient matrix has a pivot entry. So that corresponds with one solution. So we would say that this particular matrix is going to have one solution. All right, let's check out another example. Let's say we have this matrix. Does this linear system of equations that this matrix represents, does it have no solution, one solution, or an infinite number of solutions? Well, let's first identify our pivot entries. So in the first row, our pivot entry is right here, this 1. It's the first non-zero value. In the second row, our pivot entry is right here. So we would say that this first column and this third column are pivot variables. But notice that this middle column right here, it doesn't have any pivot entry. So we would say that this is a free variable in our system. And we can see that when a free variable exists and the system is consistent, which this system is consistent because we could have 1 times something to equal 3. this matrix is going to have an infinite number of solutions. So we'll write infinite. All right, let's try another example. Let's say we have this matrix. Does it have no solution, one solution, or an infinite number of solutions? Well, let's first identify our pivot entries. So in the first row, our pivot entry is this 1 right here, the first non-zero value in the row. In our second row, the pivot entry occurs right here, this 7. It's the first non-zero value in the row. So notice that the pivot entry occurs in the augmented column. So that's a dead giveaway that there's no solution to this particular matrix. And another way to think about it is, if this column is coefficients for some variable, call it x1, this is x2, and this is x3, this is telling us that we have 0 times x1 plus 0 times x2 plus 0 times x3 is equal to 7. That's never possible because we can't have 0 times some number plus 0 times some number plus 0 times some number ever equal to 7. So this is not possible, or we would say it's not consistent. So we can see that there is no solution to this particular set of linear equations. All right, let's try another one. Let's say we have this matrix. How many solutions are there to this system of linear equations? Well, let's first identify our pivot entries. So in the first row, the pivot entry is this 1 right here, the first non-zero value in the row. In the second row, the pivot entry is this 1 right here. So we can see that in our coefficient matrix, remember this matrix right here, each column has a pivot entry. So that means that this particular system of equations will have one solution, because there is a pivot entry in each column of the coefficient matrix. All right, let's try one last example. Let's say we have this matrix. How many solutions are there to this system of equations? Well, let's first identify our pivot entries. So in the first row, the pivot entry is this 4 right here. It's the first non-zero value in the row. In the second row, notice there are no pivot entries because every value is equal to 0. So if we want to imagine that this column represents the coefficients for, let's say, x1, and this column is the coefficients for x2, and this column is the coefficients for x3, what this last equation right here is saying is 0 times x1 plus 0 times x2 plus 0 times x3 is equal to 0, which is perfectly valid because whatever we plug in for x1, x2, and x3, it must equal 0. So we would say that this last linear equation right here, it is consistent, but notice that free variables exist in our coefficient matrix. So here's a free variable, and here's a free variable, because neither of them have a pivot entry in their column. So with all this information, this corresponds to an infinite number of solutions, because we said the system is consistent, but free variables exist. So we would say an infinite number of solutions for this particular set of linear equations.